We're sure excited for the opportunity that we had these past weeks to work on this project. We put a lot of time into it, and we feel like we've come up with some pretty good solutions and answers, so we're excited to share that with you, and we'll let Tiffany get started.
All right, so we'll start off with the assumptions we made in optimizing a controller for an HIV, treating an HIV patient. So we started with an initial value for the healthy cells of 10 to the 6th and an initial value of 100 viruses. And the tools we used for analyzing this problem were APM and MATLAB in conjunction and LoopPro. So the objectives of this problem we decided we wanted to keep the virus level low at about 20, and then in doing that minimize the amount of antiviral used in order to minimize the cost of treating this patient, and also have a consistent dosage schedule.
Yeah, and so right off the bat when we got the model and we tried to we thought about all the principles we've learned in class, and the first thing we wanted to do was fit it to a first order plus dead time model. And so, as we were doing that, we came to realize that this system was right at the stability point. There was a 0 on the right side, but it was also canceled out by a pole, so there were still some stable points, but it was pretty hard to get a step test and have it not, go out of control. So what we decided to do was we ended up manipulating using the virus as our manipulated variable and having the antivirus going in as the control variable. But then when we put that into LoopPro, we switched it around and said that the antivirus going in was the manipulated variable and the virus was the controlled variable. And then we tried to fit it to first order plus dead time model right here. And as you can see, it wasn't too great of a fit at all. But we went with that for our first, to calculate out our first control parameters. And then what we also wanted to do, because we tried a bunch of other ways to get control parameters, but what we ended up falling back on was finding out the state space model and using that transfer function to figure out ranges of gain values that would work for this controller. So we did, we figured out what the steady state value was at 20, 50, and 100, and then using root locus plots we were able to find the range of KC that would work and make the system stable and be able to control it how we want it to. And then this next slide will show you what happened as we fit our controller.
Yeah, so we first tried to just keep the virus level at 100. And when we did that, we found an optimal solution with a moderate gain, a low time constant, and the total antiviral used was pretty high. It was almost 30,000 units. And so we thought, we could probably limit the amount of antiviral used and optimize the cost of the treatment plan. And so what we did from there is instead of keeping the virus at 100, we dropped it immediately to 20. That seemed to work best. We tried also dropping it to 50 and then 20, but just going straight to 20 worked out best for minimizing the amount of AV used. And so when we did that, we actually came up with this model, and you notice that the controller gain is actually outside of the stable controller gain limits. And you can kind of see that the amount of antiviral you need to use is oscillating, and it's actually getting bigger as you go forward through time. And we thought, that's okay for this 10-year system, but it's going to be pretty hard on the patient and the doctor to try and keep up with this kind of oscillation. And so we decided to sacrifice a little bit of the cost in order to make the treatment schedule a lot easier for both the patient and the doctor to follow. And so what we did is we changed the controller gain and the time constant so that we can keep the virus level at 20 with about the same amount of dosage over a long period of time. And so you can see that we need a lot of antivirus at the beginning, but then over time it flattens out.
So just to wrap things up, we decided on a model where we had a very aggressive gain, where Kc actually equals -42, and a longer time constant of 0.2 years as opposed to the 0.02 which we were using before. This allowed us to come up with a more consistent treatment plan at the cost of slightly increasing the amount of antiviral used, so that we could keep the dosage levels consistent over time without having spikes, which would be difficult for the patient to handle.